Hello students, in the previous video session we already discussed about data hazard. A data hazard is a situation in which the pipeline is stalled because the data to be operated on are delayed for some reason. So in the present video session we'll discuss about instruction hazards, and here we'll see how exactly the pipeline is stalled because of instruction hazards. So first we'll take overview. Whenever the stream of instructions supplied by the instruction fetch unit is interrupted, at that instant pipeline stalls may occur. So this may be because of cache miss or else branch instruction. Either a cache miss or a branch instruction stalls the pipeline for one or more clock cycles. So the instruction will be fetched, it will be delayed by one or more clock cycles. To reduce the effect of these interruptions, many processors employ sophisticated fetch unit that can fetch instruction before they are needed and put them in a queue. So usually we can fetch the instructions in advance and we can copy the instructions within a single fetch unit, sophisticated fetch unit, and from the fetch unit the instructions can be fetched in a sequence before they are needed and put them in a queue. Typically the instruction queue can store several instructions. So within the instruction queue we can store multiple instructions. A separate unit which we can call it as dispatch unit takes the instructions from the front of the queue and it can send the instructions into the instruction queue. So the instruction queue, from the front end the instruction will be dispatched into the execution unit. So execution unit, and the execution unit will execute the instruction, and finally the instructions result will be written in the respective location. So now we'll consider the unconditional branch instruction. So in the case of unconditional branch instruction, we can observe that we are having around 6 clock cycles. So the diagram shows a sequence of instructions being executed in a two-stage pipeline. So here we can observe that the instructions are executed in a two-stage pipeline operation. So that is execution phase as well as fetch phase. Instruction I1 and I3 are stored at a successive memory location, and I2 is nothing but a branch instruction. So the branch target with the instruction IK. So now I'll take the branch target. That is nothing but IK. In clock cycle 3, during clock cycle 3, the fetch operation of I3 is in progress. So we can say, observe here, during I3, fetch phase of F3 is in progress. The fetch operation of I3 will be considered during clock cycle 3. At the same time, the branch instruction will be decoded. At the same time, during clock cycle 3, the branch instruction it will be decoded. And the branch target address will be computed here. During clock cycle 4, the processor must discard I3 which has been incorrectly fetched. So during clock cycle 4, during this clock cycle, the processor will discard the instruction which is incorrectly fetched and the instruction IK. In the meantime, the hardware unit responsible for execute step, that is E step, must be told to do nothing during the clock period. Thus, the pipeline is stalled for 1 clock cycle. So here the processor will discard the instruction and during clock cycle 3, execution unit will be under idle mode, so that during this clock cycle the pipeline is stalled. So I can say that the pipeline is stalled. For 1 clock cycle. The time lost as a result of branch instruction is often referred as branch penalty. So the time lost, during which the actual execution phase is idle, so that penalty is called as branch penalty. The penalty is occurred with respect to the branch instruction, so I can call it as branch penalty. So the branch penalty is 1 cycle in the given example. For a longer pipeline, the branch penalty may be higher. So in this case, we consider the branch penalty is by 1 cycle. So here we can observe that the branch timing during clock cycle 1, the actual fetch phase of instruction 1 is taking place. During clock cycle 2, F2, but because of branch instruction, here the instruction is delayed. The execution phase will not perform any task. So that means the execution phase is idle here. So we can say that there is a branch penalty by 1 cycle. So we need to reduce the branch penalty. So in this case, we are having only one branch penalty by 1 clock cycle. In some cases, the branch penalty may be higher. So we can observe that the effect of branch instruction in some cases the branch penalty will be by 4 clock cycles or more than that. So we have assumed that the branch address is computed during E2 and instruction I3 and I4 must be discarded, and the target instruction IK is fetched in clock cycle 5. Thus the branch penalty is 2 clock cycles. So now we'll consider instruction queue and fetching phase. So the diagram shows the use of an instruction queue in the hardware organization. So here we can observe that it consisting of fetch instruction queue, as well as dispatch decode unit, and one more block which is called as execution unit. So in the diagram we can observe that the instruction fetch phase, it will fetch the instruction one after the other. So this is the instruction queue. So from the front end of the queue, the instructions will be loaded into the dispatch or decode unit, and decode unit, it will transfer the instructions into the execution phase. In between, it consisting of a smaller buffer. So this is one buffer and one more buffer. Intermediate or interstored buffers are used here, and finally the results can be obtained in the last phase, this one. To be effective, the fetch unit must have sufficient decoding and processing capability to recognize and execute the branch instruction. It attempts to keep the instruction queue filled at all times and reduce the impact of the delays when fetching in the instructions. When the pipeline stalls because of data hazard, for example, the dispatch unit is not able to issue the instruction from the instruction queue. So there may be a chance of data hazard as well as the instruction hazard because of delays occurred or any kind of delay occurred during the fetch phase. So because of data dependency, there is also one more reason for data hazard. So in the case of branch instruction, we already considered how the entire pipeline may stall because of in some cases the execution unit itself will be kept idle because of there is no instruction or there is some dependency with respect to the data. So that means during the occurrence of data hazards or during the occurrence of any branch instruction, the branch target address need to be computed, but there is a dependency while computing the branch target address with the previous instruction. Conditional branches. A conditional branch instruction introduces the added hazard caused by the dependency of the branch condition on the result of preceding instruction. So in the case of conditional branch instruction which introduces added hazard which may be caused because of any dependency which is caused with respect to the branch condition. The branch instruction occurs frequently. In fact, they present about 20% of the dynamic instruction count of most programs. The dynamic count is the number of instruction execution taking into account the fact that some program instructions are executed many times because of loops. Because of branch penalty, this large percentage would reduce the gain in performance expected from the pipelining. The branch instruction can be handled in several ways to reduce their negative impact on the rate of execution of instructions. The decision to the branch cannot made until the execution of that instruction has been completed. The branch instruction represents around 20% of dynamic instruction count in the case of programs. So most of the programs, around 20% will be the branch instructions. So now we'll take delayed branch instruction. So I'll consider the processor fetches the instruction I3. The processor will fetch the instruction I3 before it determines whether the current instruction I2 is a branch instruction. So here what happens is the processor will fetch the instruction I3, the next instruction, before checking the previous instruction, that is I2 is a branch instruction. So when the execution of I2 is completed and a branch is to be made, the processor must discard I3. So now what happens is the processor is already fetched I3, but the processor has no idea about I2, but this is nothing but the branch instruction. So this is nothing but the branch instruction. So now what exactly the processor does is the processor will discard I3. The processor will discard I3 and fetch the instruction at the branch target. So branch instruction, always we have to take branch target address here. So now the processor will start executing the instructions from the branch target address. The location following a branch instruction is called as branch delay slot. That is called as branch delay slot. So the location following a branch instruction, which is called as branch delay slot. There may be more than one branch delay slot depending on the time it takes to execute a branch instruction. So if we are having two branch delay slots in the program, one slot will be with respect to the previous branch instruction, and the branch delay slot will be with respect to the second branch instruction. So the instructions in the delay slots are always fetched and at least partially executed before the branch decision is made and the branch target address is computed. So a technique called as delayed branching, which can minimize the penalty occurred with respect to the branch delay slot. The actual idea is very simple. The instruction in the delay slots are always fetched. Therefore, we would like to arrange for them to a fully executed fully executed or not the actual branch is taken. The actual objective here is to able to place useful instructions in these slots. If no useful instructions can be placed in the delay slot, these slots must be filled with no operation instructions. So if you are not having any instructions, so I can take such slots as NOP. Delayed branch instruction. So in the case of delayed branch instruction, we can observe that we are having case 1 as original program and the case 2 as reordered instructions. So in the instruction sequence, we can observe that we are having register R2 which is used as a counter to determine the number of times the contents of register R1 are shifted left. For the processor with one delay slot, these instructions can be reordered as shown in the diagram. So the shift instruction is fetched while the branch instruction is being executed. So what we are doing is, so the shift instruction will be fetched whenever the branch instruction is taking place. After evaluating the branch condition, the processor fetches the instructions in the loop, within the loop or at next. Either it can fetch the instruction considering loop or next label depending on whether the branch condition is true or false. By considering, so we have to perform left shift operation whenever the branch instruction is taking place. After that, the processor will evaluate the branch condition and it will fetches the instruction either from the program label loop or next depending upon whether the branch condition is true or false. By considering the branch condition is true or false, branch condition is true or false, the processor will fetch the instruction from loop or next. In either case, it completes execution of shift instruction. The sequence of events during last two phases in the loop is considered in the example. Pipeline operation is not interrupted at any time and there are no idle clock cycle. I can say that there is not even single free clock cycle is available if you are overlapping the operations. Logically, the program is executed as if the branch instruction were placed after the shift instruction. That is, the branching takes place one instruction later than where the branch instruction appears in the instruction sequence in the memory. So hence the name is given for such branch instruction like delayed branch. Delayed branch. So here in the case of a delayed branch instruction, branching takes place one instruction later where the branch instruction appears in the instruction sequence. Where exactly the branch instruction is appeared but will delay it by one cycle. So that is called as delayed branch instruction. Delayed branch instruction. Execution timing showing the delay slot being filled during last two passes through the loop in the figure. So here we can observe that we are having the instructions, some set of instructions. So this is in order to decrement the value, fetch phase and execution phase, and branch, fetch phase and execution phase. But here we can observe that we are having the delayed branch instruction which is coming to picture because of the condition or the branch instruction which is taking place during the second cycle. During the second instruction, that is during second clock cycle, the program is executed as if the branch instruction were placed after the shift instruction. The branching takes place one instruction later. So here we can observe that actually the branch instruction is taking place here, this cycle, during the second clock cycle, but the actual execution of or fetch of branch cycle will be delayed by one clock cycle. This one delayed by one clock cycle, see here, but actually the branch execution fetch phase will take place during this clock cycle. So this is called as delayed branch instruction. So actually the branch instruction is fetched here, but it is delayed by one clock cycle. Actual fetching of branch instruction takes place during third clock cycle, that is called as delayed branch instruction. So similarly, delayed slot, here also we can observe that here also actually the instruction is fetched here, but actual instruction, this particular time slot is simply wasted and the actual fetch phase will take place during the next clock cycle. Clock cycle 5. During clock cycle 5. So now we'll take one example. Here we can observe that the incorrectly predicted branch instruction, an incorrectly predicted branch instruction for 4-stage pipelining is considered here. 4-stage means fetch phase, decode phase, execution phase and write phase. The figure shows a compare instruction followed by a branch instruction. So the first instruction is compare instruction and here it is branch instruction. The branch prediction takes place during clock cycle 3. We can observe that during clock cycle 3 the branch prediction will takes place. This one, branch prediction will takes place while instruction I3 is fetched. Here the branch prediction is taking place. Similarly, I3 instruction is fetched. The fetch unit predicts that the branch will not be taken. What exactly the fetch unit does? The fetch instruction fetch unit it will predict that instruction, that means the branch instruction will not be taken and it will continue fetch of the next instruction also, that is I4. The fetch unit will think that the branch instruction will not take place, the branch will not be taken and it will fetch the instructions I3 as well as I4 and it will enter into the decode stage. The result of the compare operation are available at the end of clock cycle 3. So here will be having the result of compare instruction. Assuming that they are forwarded immediately by the instruction fetch unit, the branch condition is evaluated during clock cycle 4. Depending upon compare instruction, branch instruction works. So now the branch instruction will be evaluated during clock cycle 4. At this point, the instruction fetch unit realized that the prediction was incorrect. So now the instruction fetch unit, it will realize that the actual prediction was wrong by the instruction fetch unit. So instruction fetch unit wrongly predicted that the branch will not be taken and it's already fetched instruction I3 and I4. During clock cycle 4, the actual branch instruction will takes place. So at this point, the instruction fetch unit realizes the prediction was incorrect and the two instructions in the execution pipeline are purged. A new instruction IK is fetched from the branch target address. So branch prediction. Better performance can be achieved if we arrange for some branch instruction to be predicted as taken and others are not taken. Use hardware to observe whether the target address is lower or higher than that of the branch instruction. Let compiler includes a branch prediction bit. So far, the branch prediction decision is always the same every time as a given instruction is executed. So that is called as static branch prediction. So if you are predicting the branch instruction in advance, so we can reduce the branch penalty which is associated with the conditional branches. So in the case of branch prediction, we can predict the branch instruction so that we can attempt to predict whether or not a particular branch will be